All right, here we are at section 8.5, partial fraction decomposition of a proper fraction. So you will use systems of equations to solve these. These are going to be important when you get to calculus. So we'll just scratch the surface here, explain the definitions, the rules, and how we do this, and hopefully when you see it in calculus, you'll have a memory how to do it. So what we're looking at doing is we are going to take, it's kind of like a Jeopardy question. You got to write your answer in the form of a question. You're going to be given the answer, a fraction that was added or subtracted together. And what we want to do is we want to break it down to the individual fractions that were added and subtracted together. So if we have a rational function denoted as n of x, this is your numerator over your denominator, what we want to do is factor the denominator into all of its possible linear binomial factors. And then in the numerator of each individual fraction, we're going to put this capital A, which represents the constant over this linear function. And it's important to understand here that these are proper fractions, which means the top degree, a constant, which is a degree of 0, always is 1 less than the degree of your linear factor on the bottom. So this is x to the first. And so this is a constant. So capital A represents a constant matched up with x minus little a plus capital B, a constant over the linear factor x minus little b, and we can go all the way out to 26 letters if we want, but that would be crazy. Okay, so this is how we build what the, if you will, question looked like from the answer that you were given. Now, it is possible that your denominator has a binomial factor, say x minus a, that's raised to a power because it repeated. All right? Well, if that happens, then the binomial has to have a fraction for each possible power that's an integer. So if I say, for example, I had x minus a to the third power, that's what my denominator factored to. Then I need a fraction with x minus a to the first power, an x minus a squared, and an x minus a cubed, with all of these would be 3 individual variable constants that I'm trying to look for. All right, so numerically, let's say this. Let's say the answer is 7/8. Okay, well, what are the possible fractions that you could be adding together? Well, since 8 breaks down to all 2's, 2 times 2 times 2, you could have a denominator that's a 2. You could have a denominator that's 2 squared, which is 4. And you can have a denominator that's 2 to the third, 8. So in essence, you could have 1/2 plus 1/4 plus 1/8, which all adds up to be 7/8. Now, it's one possible answer. We could have lots more. But I'm just saying, when you have a factor raised to a power, you have to cover all possible bases. And if you don't need one of these binomials in your fraction, your constant at the top will be a 0. Okay? And if it goes higher than, say, 3, it keeps going all the way up to maybe the 6th power, you need 6 fractions for that one binomial factor. All right. Now, the next thing we're also going to look at, besides being 1 degree less than, it's always 1 degree less. Always, always, always. And your capital A, B's, through C's and D's, E's, F's, and G's, all those are going to be your constants on the top. We can have a quadratic factor. All right, so if I have a quadratic factor, so this trinomial does not factor. It's considered prime. All right, could have like x squared plus 1x plus 1. or x squared plus 8, something that doesn't factor. Then notice that the top numerator, again, having to be 1 degree smaller. So since this is x squared, 1 degree smaller means this is x to the first. So you're going to have a capital A as a coefficient in front of the x and plus a capital B for the constant of this linear numerator. And for every quadratic you have, you're going to need 2 terms on the top. And again, as we said earlier, if a quadratic is going to choose to repeat, then that trinomial is written to the first power, the quadratic factor is written to the second, all the way up to whatever we need. And each numerator is a linear binomial in the top. All right. So one thing I like to say is the following. Notice the pattern. X to the first, 1 term on the top. X squared, 2 terms on the top. If this was x cubed and it was a polynomial with an x cubed, you'd have to have 3 terms on the top. You would have a quadratic up there. But we're not going to go that far. All right? Okay, so there's the definition of our